Hey, what's going on, everyone? I've got this Remington Titanium model R-960 shaver that doesn't work anymore, and I thought I'd make a repair video. Then I decided instead of repairing it, I'm just going to redesign the whole circuit. Now, there's a couple of reasons for that. There's a couple things I don't like about this, the way it is. First of all, it plugs into 120 volts AC directly. So here's the power connector. There's no wall wart or anything like that. It's just 120 volts going directly into this thing. And now I don't know about you, but I don't like shaving with 120 volts on my face. So in the bathroom, there's a lot of water and anything can happen, right? I do have GFCI outlets, but I'm going to redesign it to run on 5 volts DC. And I'll put a USB port here, and I'll be able to run it on my run it and charge it on my phone charger. Second thing is the batteries in here are two AA NiCad batteries. Each battery is 1.2 volts, so that means it runs on 2.4 volts. And 2.4 volts is the low end of this motor. It's pretty slow, so it works okay when you have it plugged in. I think when you plug it in, it's running at like 3.2 volts. But when you unplug it and you're using batteries, the most you're going to get is 2.4 volts. We're going to replace those batteries with one of these LiPo batteries here. So let's see if I can zoom in. So this is a 3.7 volt, 600 milliamp hour LiPo battery. And so 3.7 volts is a lot higher than 2.4. So it'll run really well on that. Actually, we're going to drop that a little bit and maybe run it at like 3.2 or 3.4 volts. But the 600 milliamp hour is perfect because I think this thing uses around 300 milliamps. So it should work fine. Let's start by taking it apart. All right, let's take this off and let's see where. I'm pretty sure there's a screw here and there's another screw there. So let's start there. I think it only has 2 screws. Oh, that's in there pretty good. Let me get another screwdriver. Let's see here. This should work. Yeah, there we go. Okay. And there should be another screw in here. This is the NiCad warning. But we're going to get rid of those batteries, so let's just go through it. We don't need that sticker. Okay, there we go. Let's open it up. That should be it. I don't think there's any more screws. Maybe there is. Let's see. No. Let's try to pry it open with a screwdriver. There we go. And there we are. So you can see the 2 NiCad batteries. Some water's gotten in here, it looks like. That's why I don't like having 120 volts right next to my face. I don't see any. Oh, yeah, there's some corrosion down there, but it doesn't really matter. We're going to get rid of them anyway. Okay, so these batteries, let's see. Yeah, there's corrosion. So here's the batteries. Okay. And yeah, these batteries always leak after so many years. All right, so let me cut those out. Just take them out of here. It doesn't really matter. We're gonna redo this whole thing anyway. All right, so here they are, NiCad batteries. The voltage is not on here, but I know they're 2.4 volts. So these need to be recycled. You can't just toss them in the garbage. All right, let's get this circuit board out of here. There's a couple screws right here. Okay. Okay, so here's the board we took out, and we'll go over this in detail, but we're not going to use it. We're going to design a new one, but we're going to make the new one same shape as this one. Now notice here that the switch, this switch here, on-off switch, has these contacts that rub against here, right? So when those connect to that, when you turn it on, it goes up here, connects that to that, and that's what turns it on. So we'll have to design our board to work with that switch. So we'll need these. We'll need to put these pads on our board also. So now notice these two LEDs here, the low battery indicator and the charging indicator. That's these right here. Those are here and here on the board. Let's see if I can zoom in. So they're right there and right there. So when we design our board, we'll have to put LEDs there as charging indicators. Alright, so I got some bad news here. This motor's dead. I hooked it up to my power supply, and I'm giving it like 3 volts. There's nothing going through it. So it's probably dead. I'm probably going to have to get a new motor. So I'll pick up this video as soon as the new motor comes in. Alright, so I took the motor apart. It was all rusted on the inside, so some water did get in there. I was able to clean it out. Let me turn on my power supply. So it is working. Now it's drawing 600 milliamps of current right now, which is too high for this motor. And if I put the top on, let's see what happens when I put the blades on it. Let me put these on. Okay, now let's try it. It doesn't go on at all, and the power supply shows that it's drawing nearly 700 milliamps. So the motor has stalled. I don't think it has enough power to work. There's nothing wrong with these. These work just fine. I can turn them, no problem. The blades are fine. So it's the actual motor that's messed up. Alright, so while we wait for the new motor to arrive, we can begin redesigning the circuit using KiCad. Alright, so we're going to create the schematic, and we're going to do the USB portion of it first, and after that we'll do the battery part. So let's start by adding our power rails. So we're going to add our 5-volt rail first, okay, and we'll add our ground rail also, our ground. Alright, now in KiCad you have to put power flags on your power nets, so KiCad knows that these are driven. So let's do that. Let's put one on each. Okay, and then we'll connect those. Alright, so that's done. Let's put that out of the way. Now we can use those rails, and KiCad will know that they're power because we defined that down here. Okay. Alright, so let's add some of our parts. We know there's a motor, so let's add that. The motor is not going to be on the PCB, but we're just going to add it so that we can see it. Now we want this 5 volts to be around 3.4, 3.5 when it gets to the motor, so we're going to have to drop some voltage. So let's add a couple of diodes. We'll add a 1N401. Okay, and we'll put that right here. We'll add 2 of these actually, because we have to drop the voltage by 1.5 volts. So let's just add 2 of them. Alright, we'll add an electrolytic capacitor. Let's see, capacitor polarized. Here we go. Okay, all right, and let's add a ground down here. All right, so far we're getting there. Now we want to add a switch to turn the power on and off to the motor. Now this is a switch that's already on the device. It's not going to be on our circuit board, but we want to visualize it. So I'm going to add a single pole, single throw switch on here. Okay, and we'll put that right here. Okay, and we'll move the motor over. Okay, let's connect that up. Okay, good enough. This motor is going to ground on the other side. So let's put that there. Alright, so we want to have a flyback diode across this motor. So let's do that. I think I'm going to pick a 4148 for that. And we'll put that here. Alright, and we'll connect that. Okay, so another thing I want to do is put a capacitor across this motor. So let's just do that real quick too. And now you don't really need this, but I'll tell you why I'm putting it in a second here. Let me just get it on there. Put another ground. Now you don't really need this capacitor, but we may need it. And here's the thing. This motor spins really fast. I haven't tested it, but these go about 5,000, maybe they even go up to 10,000 revolutions per minute. You know, every time it's spinning, the brushes in the commutator basically they connect and disconnect every time it spins, right? So you know, 5,000 times per minute, that's a lot of switching noise. So you put this up next to your radio and you'll get a lot of interference. So we put a small 100 nanofarad capacitor here to take care of that. Actually, we put the capacitor directly across the terminals of the motor. We won't put it on the PCB, but I'm going to leave this here just in case we want to add another capacitor for another reason, which I'll go into later. Alright, so another thing I want to do is put a couple of net labels, one before the switch and one after. Remember, this switch does not go on the PCB, so it's not going to be there, but we have to have pads for these two contacts. So we're going to put a couple of net labels here because those pads have to be, we have to call them something. So let's put a net here, and we'll call this motor switch 1. We'll put it right there. And then we'll put one here. We'll call it motor switch MS2, right? And that's on the other side. All right, and let's connect them here. Just like that. Okay. This way we can refer to them, this part and this part on the PCB. All right, so now we have to annotate these because you see how they have question marks. That's not going to work. So we're going to click on the annotate so it could annotate them for us. Okay, and now you see how the question marks went away. It's D1, D2, C1, C2, and so on. Now these capacitors, we have to give them values. So right click, properties, edit value, and we'll make it a 100 or yeah, 100 microfarad. That's fine, 100 microfarad. Okay, and then this one, we'll make it 100 nanofarad for now. We may change that, but we'll see when we get to it. Alright, so that's good. Now, here's the thing. When we do our PCB, we don't want to get errors because this switch and this motor have no footprints, and we don't want them on the PCB. We have them in our schematic just so we can see them, right? So what we do is we right click properties, edit properties, and we put a pound sign in front of the reference, and that tells KiCad to exclude this from the PCB. Okay, so properties, edit properties, and exclude the motor. Alright, now this should be it for that circuit. Alright, so now we are going to add the battery part of the circuit. So let's add a battery first. Let's see here, it's a single cell battery, and we'll put it down here. Alright, so let's set the battery to 3.7 volts. And now the way this is going to work is when you have this plugged into USB, the battery will not do anything. This will supply the motor. When you unplug it, the battery will then take over and power the motor. So in order to do that switching, we need a transistor. So we're going to use a Mosfet to do that for us. Alright, so let's add the Mosfet. And the one I'm going to use is the IRLML 6402. So let's add that one. And this is a P-channel MOSFET. And the reason we're using a P-channel MOSFET is because we're going to use the 5 volts USB to control the MOSFET. So this MOSFET will basically turn on when the USB voltage goes to 0. So let me rotate it and move it over a little bit. Alright, so we're going to connect it to the battery. Let's move it over a little bit here. Put it right there. And now we're going to connect the other end to this side of the switch. So it's going to go up right here. Alright, and oh yeah, I have to put a ground over here. Yeah, we have to ground that side of the battery, so okay. Now on the gate, we have to connect the gate to the 5 volts because that's what's going to turn this thing on and off, right? So let's put 5 volts here, 5 volts right there, okay, and we'll connect that. Alright, so here's what we have. When we have 5 volts coming here, this will be off, so the battery does nothing. So the 5 volts will supply the voltage, will supply the power for the motor. When this gets unplugged, then this 5 volts is no longer here, so this turns on and allows the battery to supply the motor. Now we have to add a resistor here and pull this to ground, because when this turns off, we have to make sure the gate is pulled down to ground, or else it'll just float and nothing will happen. So let's add a resistor there and connect it to ground. We'll use a 10K resistor to pull it down. Alright, so let's get a resistor, and we'll put that here. Okay, and then we'll get another ground, and we'll put that here, and we will connect it to the gate. Okay, and that is it. So when this turns off, this will be off and it will be pulled to ground. So remember, this is a P-channel MOSFET, so when the gate gets pulled to ground, it will conduct. So then as soon as this goes off, the gate gets pulled to ground and the battery goes into action and powers up the motor. Okay. Alright, let's talk a little bit about this MOSFET that I chose for this circuit. I've got about 300 of these in a reel that I purchased off a surplus distributor on eBay. I got a good deal on them, so that's one reason I'm using them. The other reason is because it's actually perfect for this kind of circuit. So the maximum drain to source voltage is -20. Okay, let's look at here. Maximum ratings, -20 volts. The maximum current is 3.7. We're not going to be anywhere near that. We're going to be at 5 volts, and the max current will be 600 milliamps. So we're good with that. Now let's go down here and look at the threshold voltage right here. VGS gate threshold voltage. Now I'm going to use the maximum here, -1.2, and what that means is the gate to source voltage has to be -1.2 or lower for this thing to turn on. So if we look at the symbol, okay, our gate will go to the 5 volts USB, right? The source goes to the actual battery, and the drain is going up to the other side of the switch. So the source will always be 3.7 volts for us. So when we have the gate hooked up to the 5 volt USB and the thing is plugged in, then the gate to source voltage will be 5 minus 3.7, it's 1.3 volts. So this will be off. Now when we unplug the USB and this gate goes to ground, and we have 0 here, then we still have 3.7 volts from the battery at the source. So gate to source voltage will be 0 minus 3.7, so that's negative 3.7. And with negative 3.7 between gate and source, we are well within our gate threshold voltage of -0.4 to -1.2. So that's when it will turn on. Alright, so let's see what the problem with this circuit is. So let's assume for a minute that this switch is in the off position, right? And you plug this into the USB, some type of phone charger or something with 5 volts. Or let's assume that you plugged it into a higher supply, like maybe 7 or 8 volts somehow. You put a barrel jack instead of a USB in your design, and you plugged it into an 8-volt adapter, let's say. Whatever, let's just pretend that the voltage is higher and you get like, let's say you get 4 or 4.5 volts here, right? What's going to happen? Well, if you look at this MOSFET here, there's a body diode inside this MOSFET right here. So what's going to happen is if this voltage is higher than the battery voltage, you're going to get current flowing into the battery. So when you plug this in, if that voltage is too high right here, you're actually going to get current backflowing into the battery, and you're gonna be charging the battery without wanting to charge the battery, right? So if you plug this into the wall and it's off, that battery is going to continue to charge. It'll keep going even after the battery is charged, and it'll ruin your battery. So we want to prevent, the bottom line is we want to prevent current from going backwards through here into the battery, right? Because that'll flow even when the MOSFET is turned off, because it'll go through the body diode of the MOSFET. So what we have to do then is there's 2 options actually. One is we could put a diode right here that only allows current to flow up this way. The problem with that is that diode will also have a voltage drop, and when we switch to battery power, we're going to lose another 0.7 volts across this diode. So you'll get maybe 3 volts if you're lucky going to the motor on a battery power, and we don't want that. Remember I said at the beginning I didn't want that. I want to go have at least 3.4, 3.5 volts going at the motor from the battery. So a different way to do it, instead of using a diode, is to use another MOSFET. The exact same MOSFET, but in reverse. So let's do that now and I'll explain it. Alright, so let's get rid of this, and let's put another MOSFET right here, the exact same one. Okay, we'll put it right here, and let's see, we want the diode to be facing upwards. So let's see here. Yeah, so we have to flip it. Let's see, orientation. There we go. That's what we want. Okay. So notice this diode is going upwards. So it's like having a diode here, right? So it'll prevent current from flowing this way. And that's exactly what we want. So let's see, let's put this here. And we will connect it here. And we connect this to here, okay? And then this side here just connects to the other gate. So we'll just put it right there, okay? So let's see how this works. When you plug this in to 5 volts, nothing will go this way because, first of all, these gates will be at 5 volts, so the MOSFETs will be turned off, right? And then the body diodes will not conduct because this body diode on this MOSFET that we just put in there is facing this way, so no current can flow through that either. So we've eliminated the current going into the battery, okay? Now, when you unplug this, okay, the gates will both go to 0. So both will conduct. So that part still works the way it did before. The battery will be able to power this when it loses the 5 volts USB. So this works, and the reason this is better is because you don't get that 0.7 diode drop here. If we would have put a diode, you would have had a diode drop. And the reason you don't get it is because when this voltage goes away and these gates get grounded, the MOSFET conducts through here. It bypasses the diode, okay, because the gates are turned on, right? It's only when the gates are off that the diode comes into play. So this works. You'll have no voltage drop. Actually, you'll have a very small voltage drop because I think these have a 22 milliohm RDS on resistance. So if you figure it out, it's going to be like a 0.01 voltage drop, which is like nothing. So you'll still have just about at least 3.5 volts up here. So that works fine. All right, so after looking at the data sheet and seeing that the VGS threshold voltage has to be negative 1.4 or less for these MOSFETs to turn on, you're probably wondering, how is this MOSFET here even turning on? Because this voltage here will be 0 when we unplug it, and the gate will be 0. So that means the source of this MOSFET is 0 volts because nothing's going to it, and then the gate is 0 volts because we grounded it by unplugging this. So the VGS of this MOSFET is 0, and 0 is not less than negative 1.4. So how is this MOSFET even turning on? So let me tell you what I think is happening here. We have 3.7 volts here, and the gate goes to 0. So we know this MOSFET is turning on, okay, because the gate is 0, the source is 3.7, so VGS is negative 3.7. This is going to turn on. So you're going to have 3.7 volts on this side also, right? Now, that means that you're going to have 3.7 volts on this drain of this MOSFET. It's not on, but you're going to have 3.7 volts here. That's going to cause this diode to be forward biased. So you're going to have 0.7 volts across this diode. And that will put 3 volts up here, the remainder of it, of the 3.7, at the source. So what happens is, because you're getting that 3 volts up here, because the diode is conducting even though this MOSFET is off, as soon as you get that 3 volts up here, you're going to have VGS is negative 3 because your gate is 0, and now you have 3 volts up here. So 0 minus 3 is negative 3. So this MOSFET at that point will turn on. And once it turns on, this diode is out of the picture, and the MOSFET just stays on. And now they're both on. And all this happens in a split second, really quick. That's why this MOSFET is turning on. All right, so I think we're done with those two things, the USB power and battery power. So the only thing left to do here is to design the battery charging circuit. And once we're done with that, everything will be complete. So let's do that next. Okay, before we go on, let's look at what charging IC we're going to use to charge this circuit. So now I'm sure you've seen these here. These are the TP4056 charging module. Okay, and we're not going to use this module because you know we're not going to be able to fit it inside our little shaver. So, but what we are going to do is we're going to incorporate this chip into our charging circuit. So I do have a lot of these ICs, the TP4056 IC that I purchased on AliExpress. I bought 50 of them for, I think with shipping and tax and everything, it was under $4. So this is what we're going to use. You can get them, 50 for under $4 is it's pretty cheap. All right, so let's create the battery charging circuit. We're going to use the TP4056 IC. Now KiCad doesn't have a schematic symbol for it, so we're going to have to create a new symbol. So let's open up the datasheet. Let's take a look at the pinout. So it's got 8 pins. Also notice there's a pad at the bottom. That is not connected to anything. It's just for heat dissipation. So we'll have to pour some copper on our PCB so it could take some of the heat away from the chip, because this IC gets really hot. Alright, so let's go back to the main screen and click on new symbol editor so we can create a new symbol. Alright, so this is the symbol editor. Now we're going to create a new library to put the symbol in. Okay, and I'm going to call my library user library. Okay, alright. And I'm going to make it global. So global means I can use it on all my projects. Okay, now that's been created. Now I'm going to go create a new symbol. Okay, and here I'm going to search for the library I just created. User library right here. And all right, the symbol name TP4056. U is the designator. U means it's an IC, right? So this is an IC, so we'll leave that at U. Everything else we're going to leave it like this. KiCad created the actual symbol for us, and now we need to modify it. So let's see, the field value, we're going to move it down, and this we will move up right there. Okay, now we have to draw a box. All right, okay, and we have to add pins. So click on add pins, and pin 1. All right, so I'm going to pull the data sheet into view here so we can look at it. So pin 1 is temperature pin. So that is input. We'll call it temp, and that's pin number 1, and that's an input. Okay, so we'll put it right there. Okay, now pin number 2 is the program pin. Okay, so the pin name is prog. Pin number 2, again, it's an input pin. So we'll put that right there, and this box is too small. I can see that already. So let me make it a little bit bigger here. All right, so pin 3 is ground pin. So let's put pin 3 in there, and that would be power pin. So that's ground, and that's pin number 3. Okay, and we will put that there. All right. So I think we need to move this again. All right. Pin 4 is VCC. So let's get pin 4 in there. And again, that's power. It's VCC. Pin number 4. and that goes right there. Okay. All right, so I went ahead and made the box bigger so we could have room for everything else. So let's see what the next pin is. Pin 5 is battery, so let's add that. Pin 5 is battery, and that's an output pin. And so we want the circle to be on the right, so we'll do that because the text goes on the left. All right, so we put that here, okay, and let me make this a little bit smaller so we can see what's going on. All right, so that's that pin. The next pin is standby. That's pin 6. So pin 6 is standby. Pin 6. Okay, and that will go right there. Then we have pin 7, which is, let's see here. Pin 7 is charge. So CHRG, pin 7. Right there. And then finally, pin 8 is enable, the chip enable. Okay, so that's pin 8. And that goes right there. So I think that's it. All right, we did forget one thing just to get this right. Pin 7 and pin 8 are inverted. Okay, so we have to, let's see, select pin 7, graphic style, inverted. Okay, and pin, did I say pin 8? Pin 6 is what I meant. Pin 6 is also inverted. And inverted. Okay. All right, so we're done. And the other thing I want to do is edit this symbol to fill it with a color so it could match everything else. Okay. Now we're done. Now notice here, right here, user library TP4056. It's not saved yet, so I'm gonna save it right now. Save symbol. Right now it's saved. So we close this and we go back into our schematic. And we can bring in the symbol that we just created. So let's go here and let's look for it. TP4056. Here it is. All right, we put it right there. All right, so let's start with the power rails. We will hook up the ground pin number 3, and we'll put that right there. All right, and VCC 5 volts. Okay, right there. Now let's look at the data sheet, and starting with a temperature pin, we're not going to be using this pin, and it says right here the temperature sensor function can be disabled by grounding the pin. So we are going to ground that pin also. So let's put a ground there, and we'll connect that one. Okay. All right, let's look at pin 2. Pin 2 is the constant current setting and current monitor pin. So basically, here's what that means. Let me find the chart here. There's a chart. Okay, here we go. So if you want to charge the battery with 1 amp, okay, right here, that's 1,000 milliamps. You go based on this chart. Then pin 2 has to have a 1.2 kilo ohm resistor. If you want to charge, say, with 400 milliamps, then you need a 3K resistor on that pin. And they do provide a schematic here, a little circuit. So here it is. You can see what they did on the program pin. See how they do that? The RProg goes to ground, connects to pin 2. So this being a 600 milliamp hour battery, it's rated to be charged at half of the capacity. So we're going to charge it at 300 milliamps. So our resistor, our program resistor, has to be 4K. So let's put a 4K resistor from pin 2 to ground. Okay, so we're going to go here, select our resistor, and let's see, rotate it. I'm going to have to move some stuff around, but I'll squeeze it in there for now. right there, and let's connect that. And we did say, what did we say? We said 4K because we're going to charge it at 300 milliamps, so we're going to use 4K for that resistor. So let's change the value of that to 4K. Now let me move some stuff around. It's getting a little crowded. All right, so I moved some stuff around to make room. Now let's look at the data sheet at VCC for a second. If you look here on VCC, you'll notice that there is a 0.4 ohm resistor, and it's optional. That's why it's dotted. Now I'm gonna put a resistor in here. We don't need it. I'll explain what it's for in a minute because the data sheet doesn't really explain it. I'm gonna actually put it in, and we will just use a 0 ohm resistor if we don't need it. But in case we need it, we'll have a space for it on the board. So let me let me put it in. Okay, and we'll put it right here. All right, and let's just since this connects to VCC, let's just call it RCC. Okay, and we will default it to 0 ohms. Okay, for now. You know, this is just so we can have it on the board. If we need to put a value in there, we will. All right, so let's see what this resistor is for. So they have a 0.4 ohm resistor with a dashed border around it. The dashed border means it's optional. So when would we use it? Well, in our case, we're going to be charging our battery with 300 milliamps, okay? And our VCC is 5 volts. So this IC will provide 300 milliamps to charge our battery, and the voltage that it uses to charge our battery will go up to 4.2 volts. So if you look at the chart here, here's the constant voltage, right? So the current drops when it gets close to 4.2 volts. The maximum voltage will be around 4.2 volts. So this will charge our battery at 4.2 volts. So let's just say 4 volts for a minute. Let's just pretend it's 4 volts. So we have 5 volts coming in, 4 volts going out. So the chip, this IC is dropping 1 volt, and it's supplying 300 milliamps. So the power being dissipated across that IC is 1 volt times 300 milliamps. That's 300 milliwatts. That's not a lot of power. This IC can handle that power no problem, right? Now, if we, for example, if we had an amp of current, if we were using this setting right here, and we needed to charge our battery with 1 amp, then this IC would have 1 volt times 1 amp. That's 1 watt of power going across it. In that case, that would be too much power for this IC to handle. It would overheat. In that case, you would use this resistor to drop some of that power across this resistor so the IC doesn't overheat. So the rule of thumb that I use is if I'm going to be charging a battery at more than 500 milliamps, then I would put a resistor here. In our case, we're only charging with 300 milliamps, so this IC should be able to handle the heat no problem. We don't have to worry about it. But just in case the chip gets hot when we test it, we will leave a 0 ohm resistor in there in case we want to put one in later. Okay. All right, so the next pin is pin 5, and let's look at the sample circuit. Pin 5 is what actually charges the battery. So it goes to the battery, and they have a 10 microfarad smoothing capacitor here. So let's do that. So pin 5. Let's see. Pin 5 will go to the battery. Right there. Okay. And we are going to add a capacitor. We'll put an electrolytic, let's see, polarized capacitor right here. Ground. Okay, and that is a 10 microfarad. So 10 UF. All right. All right, so looking at the schematic again, our chip enable goes to VCC also. So let's hook up the VCC here. Okay, VCC goes to chip enable, so we want this to always be enabled. By the way, this chip can handle anywhere between 4 to 8 volts for VCC. I don't know if I mentioned that. Alright, so now we want to hook up the charging indicator and the standby indicator LEDs. So looking at the data sheet, they connect to power, and from power they go through a 1K resistor to each of the pins. So let's do that right now. Alright, that's done. So our entire circuit is complete now. So let's take a good look at it. Okay, there we are. All right, so let's create the PCB now.